Oh, thank you for inviting me. Okay, so I'm going to be talking about running both HTC and HPC applications opportunistically across private, academic, and public clouds. So after a brief introduction, I'll just remind people what EOSC and EOSC pilots are, if you're not sure already. Talk about computing in Fusion briefly. Then I'll move on to the EOSC pilot Fusion Science Demonstrator, which is the Prominence platform. And I'll talk about its architecture, data handling, workflows, and okay. So for those who don't know, EOSC is the European Open Science Cloud. By cloud, it's not a cloud as in OpenStack. It's just a group of services, software, and data, basically. So EOSC Pilots was the first H2020 project part of EOSC, which is the first phase of development and ends next month, actually. Then EOSC Hub is more about actually offering services, software, and data to researchers so they can actually start doing some work using it. So in EOSC Pilots, there were 15 science demonstrators, which are meant to show the relevance and usefulness of the EOSC Pilot services. So they're from a wide range of different disciplines, including environmental sciences, high energy physics, life sciences, lots of other things. And they're basically just small-scale proof of concepts demonstrating that you can do useful science with EOSC. So computing in Fusion. So by fusion, of course, I mean recreating the power of the sun in a small volume here on the Earth, with the eventual aim is to be able to create useful electricity. So in the Eurofusion research community today, they're basically just lots of very small islands of data and computing resources, and it's difficult to access data and resources at other sites. So if you want to access data from a particular fusion experiment, you have to get access to their cluster and SSH to it and do things like that. And the software is generally not portable, which I'll come to in a moment. But things are changing with the ITER, which is the largest fusion experiment ever built, which is currently being built in the south of France. This is going to generate petabytes of raw data every day, which is much more than the fusion communities had to deal with in the past. So data will need to be distributed globally, and there will need to be an access for more computing resources. So in the Fusion Science Demonstrator in the EOSC Pilots, what we're aiming to do is just to address a small part of the computing problem in Fusion, is just how to make use of academic and public clouds for Fusion HPC applications, how to extend small-scale on-premises clusters to deal with bursty workloads, those in bursting to different clouds, and then how to get the same results wherever you run. And to begin with, we're not worrying too much about data management, but we've done a little bit of work in that area. So the project is called Prominence because, well, prominence is plasma bursting out from the sun, and prominence is about bursting out from local resources into clouds. So basically what I want to do is to be able to run different types of batch jobs in clouds. And there's a huge number of different ways of doing this. In fact, probably almost everyone has invented some way of provisioning resources on the cloud to use for a batch system. There's sort of three categories, I would say. There's the cluster on demand, where you basically just spin up the entire traditional batch system in the cloud, and then people SSH into some random VM and then use it as a traditional batch system, essentially, with NFS storage as usual. The other approach is cloud bursting, where you have a standard cluster on premises, and then you set up like a VPN to a cloud and have some worker nodes in that cloud which can access data from your local NFS server, and users can just log into their normal login nodes and access the cloud, and some resources just happen to be in the cloud. And the third approach is the sort of more cloud-native approach, where there's some type of message queue database and worker nodes running in a cloud or on Kubernetes or something, and people just interact with it using a REST API or whatever. But the problem is in EOSC Pilots, we only had access to lots of very small clouds. So in particular, we're getting only opportunistic use of EGR-fed cloud sites. So the problem with this is that we're just getting sort of small numbers of cores here and there, and only for very limited time periods. And that's not the sort of problem that people had looked at in the past. So existing tools basically were about assuming you would have one or two clouds with essentially infinite resources, and that's what you had to worry about. So they would generally support multiple cloud APIs, but not simultaneously. And then the newer, more cloud-native job and workflow management systems also had similar problems in they support multiple cloud APIs, but not many small clouds at the same time. And in particular, didn't support, for example, multi-core, multi-node MPI jobs, or even jobs with different amounts of resource requirements. So in the project, we developed a service called Prominence, so the theme is basically submit globally, run globally. So this is what enables users to run their applications transparently across actually both, as well as clouds, HPC facilities as well, which could be either local or remote. So users interact with it as a REST API using JSON, but they could use either a simple command line utility that makes it appear like a normal batch system, or it could be just directly through Python or a Jupyter notebook or whatever. And then the Prominence platform is then sends out those jobs onto a variety of different types of clouds and HPC facilities. And for the users, they don't even know at all that it's running in involves lots of clouds. To them, it just looks like a batch system. So the challenge of Fusion software is that it involves lots of different languages. So for example, Fortran, C, C++, Python, Perl, RDL, MATLAB, and some applications actually include all of those together. They include some commercial software like the NAG libraries, RDL, MATLAB, involve different compilers, some of which are commercial. Plus, they're designed to be basically built and run on only a few specific clusters. So they make use of extensive modules in the pre-installed software, and if you want to try and run it somewhere else, you basically have to get the developer to come and spend several weeks or longer trying to get it to work. So it's difficult to get it to work anywhere but sort of one or two places. And the applications we want to run have a very wide range of resource requirements. So as well as science, there's engineering applications as well. So it's like plasma modeling, materials research, engineering and design, rendering, and then each application could need like one core or like over 1,000 cores. So obviously the next question is how to run the software reliably across multiple clouds. Some people attempt to set up systems that enable you to install software dependencies in VMs on different clouds, but that's something that we don't even want to consider. We'll just use containers because, as everyone knows, that will be far simpler. So we create a container image with the application and all its dependencies. So then we can have the jobs reliably run anywhere, and the jobs can be reproducible, which is not really what Fusion people have today. For the container runtime, we're giving at the moment people two options, Singularity or uDocker, which have both been mentioned already. So the user experience, just to compare our system with standard HPC. So with HPC, people would have to upload their software and input data perhaps to the system using a login node, then SSH the login nodes and compile their codes, then submit the jobs to the batch system from that login node. Jobs then wait in the queue, and then eventually they'll run. Then they can download any output data onto the laptop or whatever, and then analyze the results. So with Prominence, it's similar, but to begin with, they need to prepare a container image or use an existing one, which, like for example, if they're using TensorFlow, they might want to use the official container image and upload it to a container registry and upload in input files. Then they submit their jobs, but rather than doing that from a login node, they can do it from anywhere. And then the jobs are run on clouds around the world automatically, and users can actually look at the standard output and error while the jobs are running if they want to. Then, just like with normal HPC, they can then download any results they need, data they need, and analyze it any further. So the architecture for Prominence is fairly straightforward. Users interact with the REST API using a token that comes from an external identity provider. The main foundation of the platform is Condor, because that provides an easy way of managing jobs across different types of resources without having to redesign lots of things yourself. We have some job hooks in Condor which interacts with the placement policy engine, which then talks to Infrastructure Manager, which is a tool from Indigo Data Cloud that is, well, it's a tool, it's an abstraction layer that allows you to deploy virtual machines across different types of clouds. So for the authentication, currently we're using AGI check-ins. So the idea is that people can use their standard institutional credentials to access the system, and which makes it very straightforward. As I mentioned, we're using Condor as the main sort of foundation because, I mean, it was designed in the 1980s, but it's perfect for cloud environments. It can deal with worker nodes coming and going. It supports worker nodes over the wide area network without having a VPN or anything like that. And it's known to work reliably at very large scales, although that's not quite so important for EOSC work. And you can use it as a database. So for example, we store lots of arbitrary key value pairs with each of the jobs, and Condor's able to do that, whereas other batch systems can't. And one important thing is it can submit jobs to remote batch systems over SSH, so that enables us to make use of external HPC resources as well as clouds. So one very important part is actually deciding where to run the jobs and where to provision the resources. So we have a policy-based resource placement engine. So this is based on an automation layer on top of Infrastructure Manager that decides what cloud to use and then handles retrying and failing and things like that. So for this, we use a software called Open Policy Agent, which we provide that's a list of all of the clouds that we want to use or potentially use. We can store status information about each cloud and then provide the policy for deciding what cloud to use. And then we have a system which then makes use of this it determines the clouds that meet your requirements, then can rank them if necessary, then can try the first cloud in the list, and if that fails, it can try another cloud, and so on. So one thing that we found important is that private clouds are generally quite unreliable. So it's very important to have lots of failure handling and deal with timeouts and backing off from clouds which fail and then retrying on other clouds. So one thing we can do is what we've called hierarchical cloud bursting. So we can preferentially use a local cloud or even a local HPC facility, but then we can burst out onto, for example, we could burst on to begin with external UK national research clouds, and then when they become full, we can move on to European clouds, and then finally move on to public clouds. But of course, if any of the clouds, if you have sort of special requirements like access to GPUs or InfiniBand or high memory nodes, it will obviously only consider the clouds that can meet those requirements. And then you don't need to look at this in detail, but this gives a rough representation of the workflow that's used for actually deploying the VMs required to run a job. So it's quite complicated. So here are just a few examples of things we can do. So the first plot on the left-hand side at the top shows just bursting from an external remote HPC cluster onto an OpenStack cloud. The plot below that shows opportunistically using about 4 or 5 clouds from EGI Fed clouds, as well as Google briefly. And then the other plot just shows using 3 different OpenStack clouds, 2 of which have different usernames and passwords for authentication. The other one has token-based authentication using EGI check-in. And in that case, the 3 clouds are in 3 different countries. So for MPI jobs in containers, the first version, we did the more standard approach where we have some of the MPI components on the hosts and then use that with the MPI applications in the containers. But the problem with that is that the MPI version on the host needs to be compatible with what's in the container. So when we had this model, we had a few specific versions of OpenMPI, and then users had to say what version they wanted. And then you'd hope that it would work with what's in their container, which it sometimes did, but sometimes didn't. So then in our second approach, we did everything in the container. So all the MPI components involved are inside the container that's provided by the user. This is why we don't depend on anything on the hosts. And so with this, we actually can support both OpenMPI and MPeach. We don't need to limit users to a few specific versions. They can use anything they want, and it has a much greater chance of working. And so far, it seems to be a much more reliable way of doing things. So as you'd expect, if you compare the bandwidth and latency in different clouds compared to an HPC cluster, obviously there's a big difference in performance. So here the blue line is from an HPC system in Bulgaria that we have access to within EOSC Hub. And then the three other lines are 3 different clouds. So you can see that obviously HPC system gives much better performance, but our view is that users are generally happier if their jobs are running compared to if they're not running. So even if there's not quite as good a performance, that's not a huge problem. Plus, we've seen a lot of Fusion applications don't actually have a huge amount of MPI communication. So it's not that much of an issue. So for data handling, so we have obviously scratch space for each job local to the node. For the MPI jobs, they have access to shared NFS storage just across the nodes that are used by individual jobs. And for more persistent data, we started off just by having sort of stage in and stage out from a central Ceph storage using the Swift API. So users can specify what input data they want, and then what output files, and then they'll be able to get temporary URLs to access the data afterwards. But more recently, we've moved to, in addition to that, having POSIX-like access. So we've tried both B2 Drop, which is part of EUDAP, so that's a sort of Dropbox-like server, so you can access data from your web browser or your laptop or whatever, as well as making that data available to all your jobs, no matter what cloud they're running on. And also OneData, which is another system for federating different storage providers, which provides similar functionality. So with these, users can access their data from jobs quite easily. And this gives an overview of, don't probably have time for that. Because we can access data from, jobs can access data, that allows us to have workflows where the individual jobs can then, in a workflow, can run on different clouds. So because the jobs can access the data that was created by previous jobs. So initial support for workflows, we make use of the DAGman functionality that's in Condor. So people can specify jobs and the dependencies between them. And then because they can specify resource requirements for each job, we can then have workflows that's, as well as being able to run on different clouds, they can have HTC and HPC steps. So just an example here, there's a single node step on one cloud, then there's a MPI job running on a second cloud, and then there's a single node job running afterwards on a third cloud. So I think makes things like that quite straightforward. And we've obviously tried lots of different types of Fusion applications, so for containerizing them and then running them on Prominence on different clouds. The hardest part is actually just being able to build the software in a container, because as I mentioned before, people are used to just using one HPC system with all the modules and the software installed, and being able to actually install all of that software and make it available in a container can be quite difficult. But so far, it's been quite successful in being able to get most things working with a little bit of effort. So in terms of summary and future work, so we've developed a platform that enables users to easily exploit opportunistically both clouds as well as external HPC resources if necessary. In terms of work in progress, we're aiming to have 2 production instances of Prominence later this year, so there'll be a private instance for us to use at Cullum. Also want to have a public instance in the EOSC marketplace, which anyone will be able to access and try out the service, but just obviously have access to a small number of resources. We want to look at integration with Active Directory, possibly via Keycloak, because we don't have an identity provider, but we do have Active Directory. We also want to look at CERN's DynaFed as a way of providing access to Ceph-based storage, in a sort of POSIX-like way, and people can also access it through their web browsers. And then finally, also look at support for CWL workflows. And that's it.